Have you asked yourself a question? To what extent can we be certain an object's position and momentum? Probably not, but this can be answered by the uncertainty principle of quantum mechanics.
Werner Heisenberg stated that the more precisely the position is determined, the less precisely the momentum is known, and conversely, which means the more uncertain you are about its position, the less uncertain you are about its momentum, and vice versa.
To understand this, we must discuss the basic concepts of quantum mechanics.
There's a ball hidden inside of one of these three cups. It could be in this cup, this, or this. This represents multiple states in which the ball is in. These states could be the object's position, momentum, and many more. But for this case, it's position. These states have a probability that are not necessarily equal. The most probable state is not always the state the ball is in. Right now, the ball is in a superposition of being in all of these three cups at once. Once observed, it collapses into one state in random.
Another way of visualizing this is by this ball game.
Very few trials give you random results, but multiple trials give you a pattern. This can be represented by a probability density. The higher the peak, the more probable it is to find it there. The uncertainty principle can be observed when you point a laser through a narrowing slit. You get this probability density. If you narrow the slit, you expect the spot to narrow, but at a certain point it starts to spread. What just happened? Well, since you limit its paths, you decrease uncertainty in position, and therefore uncertainty of momentum should increase. Since momentum is a vector quantity, direction matters. This is called a single-slit diffraction. Another concept is the wave-particle duality. Everything acts like a particle and a wave. This was first observed in light and was later observed on electrons. Macroscopic objects have wavelengths too. It is calculated by the Broglie Wavelength formula. A particle has no definite momentum but has a definite position, and a wave has a definite momentum but no definite position. We can add waves of multiple trials to have a smaller wave packet. This can be represented by a wave function. The square of the wave function is the probability density. It tells us how probable it is for a particle to be in that state. To increase certainty in position, we add more waves and thus have a large uncertainty in momentum. And to decrease certainty in position, you can add less waves. Why don't we observe the uncertainty and wavelength on macroscopic objects? It is because the Planck's constant is so small, if the volume of the sun equals 1,
Then the Planck's constant has a volume of this ball.
it is undetectable and insignificant on large objects, but is significant on microscopic objects. We can never be fully certain at one's position and momentum, or the other will be infinite. One thing's for sure, we're certain that we're uncertain.